In the previous video, we outlined how the batch normalization procedure works. In this video, we are now going to take a look at how we can use batch normalization in PyTorch. So recall, batch normalization is a procedure that we use to standardize the net inputs. So suppose here we have a regular network without batch normalization. We usually then have the path from input feature to net input to activation as follows, as shown here. And then if we use batch normalization, we have these two steps in between. Step 1 is the standardization of the net inputs, and step 2 is the pre-activation scaling. Okay, so how do we now use BatchNorm in PyTorch? It's actually pretty simple. There is already a BatchNorm class in PyTorch. We just have to put BatchNorm after the fully connected layer and before the activation function. However, note some people also prefer to put BatchNorm after the activation function, which is a choice that also works fine. By the way, you might wonder why we call it BatchNorm 1D. That's because we work with one-dimensional input features. In the next unit, we will actually talk about two-dimensional inputs, images that have a height and a width, where we will be using the BatchNorm 2D function. Another thing you might wonder about is why we have the 100 here. That's because we have learnable parameters in BatchNorm. We have the betas and the gammas. So here it's 100 because the output of the previous layer is 100 units, so we need 100 betas and 100 gammas. So remember why we talked about batch normalization in the first place. It's because it's a method that can help us with the convergence, and it can also help reduce overfitting. So here I ran an experiment where I have a network without BatchNorm on the left-hand side, and on the right-hand side I have a network trained with BatchNorm. And you can see that both the convergence is improved, so we get higher performance earlier on with fewer epochs, and also the overfitting is reduced, which is very nice. However, before we can end this video, there's one more thing we have to talk about. So in step 1 of BatchNorm, what we did is we computed the mean and the standard deviation for a mini batch. However, during inference, when we apply the neural network to new data, we may not have a data batch. We maybe only have one single data point and we want to make a prediction. So how do we actually use BatchNorm during inference when we only want to do predictions? So what we do is when we use BatchNorm during inference is that we use an exponentially weighted average of the mean and variance terms. So an exponentially weighted average is just yet another term for the moving average. So we have the moving average of the mean and the moving average of the standard deviation. Alternatively, some people like to compute the global mean and standard deviation for the whole training set and use that one during inference. PyTorch by default uses the exponentially weighted average. In order to make sure that the model works correctly during inference, we have to remember to put the model into the evaluation mode, which we have talked about in previous lectures. So in this lecture, we have seen that BatchNorm can help with convergence and performance. So now in this video, I explained how BatchNorm works, but I still haven't explained why BatchNorm works. So why BatchNorm works is actually a hot topic of discussion, and I will include some pointers and different opinions in the resource section. So now that we have seen that BatchNorm is actually a very useful technique for improving convergence and reduce overfitting, I want to introduce you to yet another technique to reduce overfitting, namely dropout. We will talk about dropout in the next video.